Well, my name is E.Cherkashin, and I would like to present my talk entitled Information Technologies for Supporting Research of Complex, Large-Scale, Resource-Driven Discrete-event Systems Under Uncertainty. We prepared this talk with my colleagues from Sh.Huiyuan University, School of Information and Control Engineering. And I personally work with my Irkutsk colleagues in Matrosov Institute for System Dynamics and Control Theory. This talk is devoted to our joint project submitted to Russian Science Foundation in this year, and we hope that it will be supported. In this talk we consider the informational technologies which could support investigations in industrial systems. Industrial systems are the union of individual manufacturing and network computational systems. The aim of this unification is to improvement of overall operation, efficiency, and reduction of consumption of raw materials. The history of automation in industry have three main points. The first one is the first introduction of industrial systems, when the manufacturing process and the IT was joined together. It was in 80s of the 20th century. In 19th, the main point of research was reorganization of existing processes. So this direction was named as reengineering of business processes. And the third point is new one devoted to collaborative manufacturing and management of process between counterparties, where the management and the science try to account the interest of all institutions which are collaborated for manufacturing. And today the main problem of modeling is the scale of the systems, because each industry can contain many branches. Due to the large scale of networked systems, it is difficult to realize traditional centralized control, which were used in the 20th century. Nowadays, control structures are large-scale network industrial processes which are decentralized and distributed. Decentralized control is simpler in structure and more convenient in implementation. Distributed control deals with coupling relationship through communication between subsystems. The quality of the communication implies the quality of control. The main our interest is to construct models which account this coupling. There are three kinds of industrial process, three kinds of models. The first one is continuous, the second discrete, and the third one, the most complex, is batch processing. Batch processing means that for each commodities the industry should construct a plan of the manufacturing, schedule, and somehow to control the process of implementation of this schedule. In this slide we have an example of batch processing. The processing consists of a number of different stages which should be organized in one complex process. The batch processing is described by various levels of details. For example, we can account only the structure of process, then we can account the schedule, and we also can account the uncertainties, for example, shortage of resources or absence stuff due to illness and so on. The aim of the modeling is to synthesize the control which will hold the system in a desired state. Let us consider the modeling approaches used in industry systems. The first one, which is basic, is discrete-event systems, which are also used in description of computer networks, resource allocation in computer cloud systems, automated manufacturing, air traffic control, robotic assembly line, and in our institute we also use it to control groups of underwater autonomous vehicles. As an industry is functioning in a computational environment, we should account the events which occur in this environment affecting the process of industry functioning. We divide uncertainties on two parts. The first one is originating from environment. The second one are originated in industry itself. The second one usually represents shortage of resources. On this slide, we represent an example of a discrete event system taken from this paper. There is a train which should pass a gate, and the model of train behavior is this patronet, and the gate is this one. These patronets are independent. That means the behavior of both objects can result in crash of a train or a gate. At the right hand side, we can see the synthesized supervisory control, which consists of adding new state and joining over the system. In this case, the train can pass the gate if it will enter the R area, and the gate will close when train enters Y area. We say that industrial system is under control if it is at a set point or its behavior in each dynamic state correspond to a set of constraints. There are four main approaches how to construct control. The first one is to construct a set of reacting rules to the generated events. It's look like expert system. In the second approach, we admit that the number of agents is infinite. As the number of agents are infinite, their impact to the system is unseen, and we can use continuous mathematical methods. The fourth one is a fuzzy and neural network methods. If an industrial system is considered as black box and we are interested in its outer behavior, machine learning methods could be used. But our main interest is to use predictive control when we have a special model which describes the system behavior, and the real system should obey. If we want to construct control for a system uncertainties of both kinds, we should use predictive control. And most of the systems based on predictive control use a receding horizon strategy of computer simulation. There are three main subdivisions of this control: is distributed cooperative control, the same with limited resources, and the same with structural uncertainties. On this slide, I try to show the main idea of predictive control with receding horizon strategy. T0 corresponds to the current state of the system, and T10 correspond to the final state of virtual future, in which we try to synthesize possible trajectories where at each point we have constraints to be satisfied. In this example, we synthesized two possible trajectories. They are possible because they finish it at the final state T10, and all trajectory points are satisfied conditions. Green trajectories correspond to the possible trajectories whose leaves happen to be non-satisfactory. If we have at least one such trajectory, then we could take its beginning as a desired control. The main problem at hand is the complexity and the scale of industrial systems. So we need to introduce in this research means of visual representation of industrial systems. And we decided to use the following technologies. It's UML, SysML, BPMN, and CMMN visual notations. We will implement two kinds of control. The first one is supervisory control for discrete event representation of the industrial system, and the second one is the same as we described above. We will use automatic theorem proving to construct these trajectories and logical theories to describe the system behavior. And also we will use resource-based games in combination with discrete event systems, and these games need to describe systems behavior in sense of resource conversion. For example, by means of this theory, we can describe the impact of counterparty activity to our industry. For example, taking over a customer or taking over a resource supplier. The resources are represented as multisets. Multisets consist of an element and the multiplicity of this element. Each element describes a resource and its owner, the player of a game. So we need to construct trajectories trending to Nash balance. The interest of each player is described by filter conditions. C1A means that resource of player A at the end of the game should be more than 2 units. To describe the actions of the agents, grammar rules will be used. For example, some action converts this set of resources in this set of resources. -1 means that the resource A of player B will be reduced by 1 unit. Left hand side defines the resources which should be spent to achieve this one conversion. The initial state is described by V0. So, by means of a resource-based game, we can describe the possible outer uncertainties of the industrial system. On this slide, we showed a model set of SysML. SysML is used to describe systems which aren't directly related to software design. But it also has some additional diagrams. For example, requirement diagram. This diagram used to describe dependencies between various requirements. This diagram, named Parametric Diagram, is used to describe models. For example, here we have model of brakes of a car. This is well-known business process modeling notation, which is used to describe imperative process case management model and notation. It's a model used to describe cases which are not imperatively defined. This model is declarative and expresses various variants of system behavior. We will use it to describe internal uncertainties. On this slide, we represented directions of adaptation existing algorithms and software to our problem. For example, discrete event system control synthesized algorithmically. We have software used to synthesize decentralized control for underwater autonomous vehicles. We already tested it. Our methods could show the structural elements which prevent the synthesis if the synthesis is not possible. In this slide, our research plan is shown. This plan is divided on two parts: ours and our colleagues from China. Their main interesting is model ethylene and polypropylene production. In conclusion, I would like to say that the software we are going to implement refers to automated research. We hope that after implementing our plan, we will gain a 3-level model, adding third one, control of dynamic of scheduling with synthesis of discrete event systems, control supervisors, and admissible trajectorials in predictive control mode. This is a relevant research topic in industry systems. This direction is referred to as Advanced Industrial Process Control. Thanks for your attention. If you like my talk, you could download it from internet. Thank you very much.